So first we discussed the limitations of the regular amplifier in delivering large power, because we have seen that regular amplifier, that efficiency, the maximum theoretical efficiency that we can have is 25%. But including the other factors like losses in the circuit, and to avoid the signal distortion, the actual efficiency we can have is actually less than 20%. So that means that 80% of total power, right, that is supplied by the battery and consumed by the circuit will be wasted, right? Will be dissipated in the circuit as heat. So if the circuit has to deliver large power, which is usually the case for output stage, right? At the output, the amplifier, they are supposed to deliver large power to the load. So then, but they can deliver only 20% of the maximum 20% of the power that they consume. That means 80% of the power will be dissipated as heat, and that is a tremendous loss, right? And also that will cause tremendous heat generation, rise in temperature, and that will deteriorate the performance of the amplifier. It will also shorten the lifetime, and it can eventually damage your circuit. So the stakes are high at the output stage for the amplifier when you need to deliver large power. So because of that, the output stage is specially designed so that we can minimize the power consumption, right? And improve the efficiency so that heat loss is minimum, and we can keep the rise of temperature under certain threshold value. And that's how the power amplifiers were developed for the output stage. And also we discussed the basic concept of the power amplifier in the last class. So the power amplifier, unlike the regular amplifier where the bus, the way it is bus, the bus can keeps flowing all the time, right? So it is constantly drawing power from the supply, irrespective of the amount of current or power it is delivering to the load. Because current fluctuates, sometimes it is zero, sometimes it reaches the peak, right? But the circuit keeps drawing the same level of bus current from the source, and keeps dissipating same amount of power all through the time during which it is delivering the power to the load. So unlike that, power amplifiers are designed in a way so that it will draw the current from the source only when it is delivering current to the load, right? And the amount of current that is drawn from the source will also vary with the variation in the load current. For lower load current, it will draw low current from this supply. For high current, it will draw high current. So it will draw the current, the amount that is needed to supply the load, right? So, so it will just draw the that amount that is needed, not more than that. So that is in that way it tries to minimize the power draw and minimize the loss, heat loss in the circuit, and improve the efficiency of the circuit. Now, and For that, we got this push-pull output stage that we discussed in the last class. In the push-pull output stage, there are basically two transistors are used. Both are in common collector configuration. One is the NPN, our usual NPN common collector configuration. The other is the PNP, or same common collector configuration. So the the reason behind using the two transistors is that only one transistor will be working during one half of the cycle. Because in this, the output stage power amplifier, the current is not supposed to flow while the load current is zero. So there is no bus current actually flowing. And usually the VBE, let's say, is very low. I mean, it's just if you look at the IV characteristics, the VBE that is supplied to the base emitter junction to forward bias the base emitter junction is same as the what we call the cut-in voltage for the diode, what the current just starts to picking up. So if you forward bias the diode with this cut-in voltage, so current that will flow through the diode will be very less, negligibly small. So we can neglect for all practical purposes, and you can say the current is zero when the load there is no current flowing into it, and the load is not drawing any current. But it will not be exactly zero. No matter how small, there will be some amount. It can be in picoampere or nanoampere range, but still there is some current flowing. But that will not affect, because that is negligibly small. I mean, compared to the current that actually flows in the circuit. So a minimum amount of forward bias voltage will be there, and that will be supplied through the what we call the circuit. That can be supplied through the two diodes to explain the concept that we discussed in the last class. And instead of diodes, actually we use a transistor, and that is called the VBE multiplier, because the voltage that is generated here, VBB, so that supplies these two forward bias voltages. So that is, we express like this, IR1, right, this current times the two resistances, right, series resistance, that is the voltage drop, VBB, and IR1 is the this voltage divided by R2, right. So there is a simple circuit analysis, and this is we finally express in this form. So this is the multiplying factor by which we are actually multiplying the VB. And by varying R1 and R2, we can adjust this voltage VB. So that's why it's called, the circuit is called the VBB multiplier. And this circuit provides the forward bias voltage to these two transistors. So they are just forward bias, just on, but carrying very little current or almost no current. So now whenever you supply a voltage, right, and voltage is positive, this transistor in PN, this will turn on, right, and current will start flow. Because this is a common collector configuration, whatever is the input, we get the same voltage at the output V naught. And since we have voltage, now current will start flowing, and the current will flow like this, right? So that is the during the positive half cycle, the load will draw current through the transistor Qn. Qn will be off, but this one will remain off. Right? This will remain on. This one will remain off. When the voltage is negative, this will turn off, right? And then with negative voltage, this one will turn on. When this one turns on, because this is also common collector configuration, whatever voltage we have here, same voltage you get at the output. Now here the output is negative, so current will now flow up, and it will flow down through this QP transistor, right? So the current will flow in the opposite direction. Now this one QN remains off and QP turns on, right? So these two transistors, only one will be operating during one half of the cycle. During the positive half cycle, Qn operates and it turns on, it pushes the current through the load. And during the negative half cycle, Qp turns on and it pulls current through the load, right? Pulls out. That's why it's called push-pull output. So one transistor will push the current through the load, another will pull the current through. So called push-pull output stage. And you see the current is flowing only when load will draw the current. And this amount of current will also, fluctuate or vary with the signal voltage. Right? When signal voltage is rising up, current will, rise. And so current will rise and fall with the, same, I mean, what do you call it? Uh, I mean, in the same sequence, right? The voltage is rising and falling. And so it will drawing the current from the source only the amount that is needed by the load, and when the load current is zero, there is no current drawn by the load, no current will flow from the source. So that is how the power drawn by the circuit is kept to a minimum level, only that is necessary, and plus little bit of, I think there will be some losses in the circuit, so for that some additional current will be drawn. So it considerably improves the performance of the circuit from less than 25% to close to 80% efficiency. And yeah, you need to provide this IR and this current, this will be flowing through the whenever load is drawing current, so this collector current and this the base current, so this current will flow. So you need to have this the current source here. So we need to design a current source that will be supplying all these components of current. And the input voltage we can apply at the base of QP transistor, or we can apply at the base of QN transistor. So whatever we apply, but we don't apply it directly, but we apply it through another common collector configuration to avoid any loss of signal. So this is another common collector configuration. We are applying VI, so that goes here. Right? So VI is like a voltage buffer. We can also apply at this end the voltage, input voltage. Is that clear, guys? Any question?
No, sir.
So here this is the output stage, and the output stage they are designed. This I will call the power amplifier. They need to handle large power. They need to deliver large power to the load, and large power means mostly the large current. So V times I is our power. So V is also usually in level of volt at the output, and maybe in previous stage it will be in millivolt, but the current will be in the range of milliampere or microampere in the input and gain stage, but in the output stage current can go very high up, maybe in the range of ampere. Right? So that is how we increase the level of power, right? So current flowing through this transistor can be very high in the range of ampere, unlike the current that is flowing in the previous stages. The current that flows in the previous stages usually in the range of not more than few milliampere. Usually in the microampere, some cases it can be in milliampere range, but in the output stage it can be milliampere to a couple of ampere. Right? So you can have very high current. So when the current is large, so the transistor that are used at the output are very different, not like the transistor that are used in the regular amplifier. So the transistor will be the size will be big, right? They'll have big size, and for heat dissipation they can have special arrangement of fins, those structure that will dissipate, they can efficiently dissipate the heat and keep the IC cool. So they are specially designed amplifiers, specially designed transistors will be used at the output stage that can handle large power. So these transistors will be very different. Their specifications, right, their construction and everything, their design, everything will be different. So that is one you have to take note of. And we can further enhance the power. I mean, if the current needed by the load is larger than this current one transistor can supply, then we can further enhance, right, the capacity of current, right, by adding one more or whatever I mean more number of stages or more transistor at the output. Okay, let's show this. Okay, so basic, this is our basic, this output stage, this power amplifier. So here we are applying the input, the load will be connected here. Now the current that the load will need has to flow through Qn during the positive half cycle. During the negative half cycle, it will flow through Qp. Right? So this current during the positive half cycle, it will flow through like this, our load current, and during the negative half cycle, flow like this. Now, if the current that is needed by the load is larger than this transistor can handle, so we can add more number of transistor at the output. We can enhance the current capacity of the output stage. So we have added one more transistor here. So you see that how it will work. Okay, first we need to do this. So let's say we have a resistance R here, small resistance R. Now this IL, so this IL will flow through this, right? So this will cause a voltage drop here, IL R, right? This causes a voltage drop. And we have put another transistor here. The connection is such, so it will have a voltage drop here, VEB, right? Plus minus. So for large current, if the load needs large current, so if ILR is larger than VEB, right? Larger or equal to this voltage. Let's say this is our QP prime. Right? We have QP here. So if current is small, so this voltage will be smaller than this. This will remain off. But if the load is drawing large current, and if the current is larger than VEB, sorry, this voltage drop gets larger than this voltage VEB, so this will turn on, right? QP prime will turn on, right? This will turn on. And when this turns on, so additional current can also flow through this, right? Let's say this is our additional current, right? So the current, the load will draw can come from both this Qn and Qp prime. And this is how we can extend the current, the supplying capacity of the output stage. So this one is for the positive half cycle, and similar structure we can have for the negative half circle. In this case, so this current here is our load current is flowing right down. Now this will cause a voltage drop here. So with this plus and minus, if current is large, so we will have a high voltage drop here. And if this voltage drops, if this voltage drop, it, I mean exceeds this base to emitter voltage, this will turn on. So that is Qn prime, and this will turn on. Then this can also pull additional load current, right, in this direction. Right? So that is how, so it can take some share of the load current and enhance the capacity, right, to supply the current to the load, right? Is that clear, guys?
Yes, sir.
Question. So that is the output stage, and here comes the input at the input side. Okay, so this current you can supply. So these are basic current source circuit that will generate some reference current, and then this current can be reproduced, right, at other places, right, like here, and that can be used to supply the current that is needed, right, for this. output stays. Similarly, here you can have your so can you recognize this circuit here? What is this circuit? Hello guys. Are you there?
Yes, sir.
What is this circuit? Can you recognize this one?
Uh,
What this with Q1 and Q2? What will be this one? This circuit with Q1 and Q2. No,
so, it's a differential amplifier, sir, with active load.
yeah, it's a differential amplifier. And that is our input space. And what is this on top of that? Let's say Q3 and
So
Q4.
Q3 and Q4.
So what is this?
So Q1,
Q3 and Q4.
It's a current mirror.
And what is their function here? Q3 and Q4, the function that they are performing.
Open the door.
Q3, Q4, what is their function? They're working as an active load, right? Working as active load. as I've discussed, differential amplifier with active load to enhance the the output resistance and the gain. And this one here is supplying the bias current, right? This current mirror is like active load for the differential amplifier, and this current mirror here is supplying the bias current. So you see the way we have designed this current source, so we can also push the current from top, or we can pull the current from bottom. So it can work both ways, right? So so that is our input stage. Then we can also have our gain stage. Gain stage we can have a common emitter, but before that common emitter, we put a common collector. We put a common collector, and yeah. Something happened. Disconnected. Or maybe better we can put it that way. Not like this. This one not needed here. There is a mistake. Okay. So this one, let's say this is our Q5. This is common collector, that is like a buffer, and this is our common emitter. That's it. The gain stage. So again we have, let's say this is Q5, Q6, Q7. Again common collector buffer stage. So we have, so that is our input stage, right? So this is our gain stage, and that is our output stage, right? So output is, this is our power amplifier. Gain stage we have common emitter, right? Before that we have common collector, and after that we also have common. So it's like common collector, common emitter, common collector configuration. Input stage we have differential amplifier, right? With active load, right? So that is a kind of our op-amp. And you can have your different structure, different design, right, for different requirement of your amplifier. There can be hundreds and thousands of different combinations. Any question, guys?
Yes, sir. Sir, can you, sir, also call the output power amplifier class AB amplifier?
Sorry.
Sir, class AB amplifier. Can you call the power output amplifier? The circuit on the right side.
Yeah, it's kind of class A. Yeah. Any other question, guys? So try to design your own power amplifier, own operation amplifier to meet different requirements. That will be a good exercise, though it's not included in the syllabus because we don't have time for that. But for your personal, practice and to develop some skills.
স্যার
Yes,
স্যার ফাইনালি সিলেবাসটা একটু বলা যাবে স্যার?
final syllabus. I mean, up to this much, and okay, we can start from differential amplifier. Differential amplifier, current source, current mirror, active load, and the output stage power amplifier.